All right, the concept of equilibrium is about when the reaction stops. What we're concerned with is when the reaction stops, how many products did we make, how many reactants did we lose? In chemistry, most chemical reactions are reversible, meaning that as the concentration of the reactants decrease and the concentration of the products increase, the products start reacting with each other to reform the reactants. And the reaction stops when the forward rate of reaction is equal to the reverse rate of reaction. So chemical equilibrium is happening all the time as the concentration of the products goes up and the concentration of the reactants goes down. There comes a point where the concentrations don't change anymore, but that doesn't mean the forward process and reverse process isn't happening. It's just that means that the rates are equal. So the concentrations of the reactants and the products don't change, and we're at the end of the reaction. So if we're looking at A turning into B, we've got a rate constant in the forward direction. If we're looking at B turning into A, we've got a rate constant in the reverse direction. So if we had a first order relationship to the concentration of A and a first order relationship with the respect to the concentration of B, when the rate of the forward reaction and the reverse reaction are equal, I could set these equal to each other. If I divide both sides by the concentration of A and divide both sides by the rate constant in the reverse direction, I end up with the concentration of the products over the concentration of reactants equal to some constant. Constant times a constant is a new constant. This constant is the equilibrium constant. And the magnitude or the size of this equilibrium constant is going to tell us how far forward the reaction went. Did we make a lot of products and lose out a lot of reactants? Or did this reaction stop pretty soon when the concentration of the products reach a certain concentration and the reverse reaction stopped the reaction without making very many products? All right, this is called the law of mass action, and it was determined experimentally. When the reaction stops, and I look at the concentration of the reactants in the products, right? So A reacting with B to form C and D. I take those equilibrium concentrations, plug the concentration of the products times each other, divided by the concentration of the reactants, raise their stoichiometric coefficients. That number that I get when I plug those numbers in is always equal to an equilibrium constant at a particular temperature. So just experimentally, this is the way it comes out. Take the concentration of the products, raise it to their stoichiometric coefficients. Take the concentration of the reactants, raise it to their stoichiometric coefficients. Divide one or the other, and you get the equilibrium constant. All right, so let's look at a system. We have dinitrogen tetraoxide turning into nitrogen dioxide. So if I start off with all reactants here, ready, set, go, I let the reaction go forward. Concentration of the reactants go down, concentration of the products go up, and there comes a point where the reaction stops. So when the reaction stops, but this particular case, I didn't make very many products compared to the amount of reactants I have, right? So at equilibrium, I have these concentrations. So if I take these concentrations, plug them into the law of mass action, all right, the concentration of the products raised the second power because I got a coefficient 2 in front of NO2. Concentration of N2O4 raised the first power, divide the reactants into the products. I get this number. So this is a small number, all right? This small number tells me that, hey, this reaction didn't go very far forward before it stopped. All right, so this time we're going to look at the same system, except we're not going to start off with all reactants. Let's start off with some products. So the question is, with these concentrations, am I at equilibrium? All right, so ready, set, go. Let's let it go to equilibrium. Let's let the concentrations change until I get equilibrium concentrations. So ready, set, go. Oh, okay, so I wasn't at equilibrium yet. The concentration of the reactants had to go down some more. Concentration of the products had to come up some more. And now I take these concentrations, plug them into the law of mass action. Now, notice, these concentrations were different from the first condition. So I've got new concentrations. When I take these concentrations, plug them in the law of mass action, I get the same equilibrium constant. So the point, it doesn't really matter where I start in this process, having some reactants, having some products, having all products, having all reactants, no products. When you let this thing come to equilibrium and take those concentrations, plug them in the law of mass action, you get the same number every time. That's why it's a constant. So let's start off with all products and no reactants. So the way this system has to shift in order to get to equilibrium concentrations is I got to lose some products, right? I've got the products will react with each other to reform the reactants, and when this reaction stops, I'll raise the concentration of the reactants and lower the concentration of the products. When I take these concentrations, plug them in the law of mass action, again, I get the same number. So this is what the equilibrium constant tells us. When I have the concentrations at equilibrium and plug them in, I get the same number every time. Or I should say the law of mass action tells us I get the same number each time. That's why it's a law. So as the concentration of the reactants went down, the concentration of the products went up, and there came a point where the concentrations didn't change anymore. Those are equilibrium concentrations. Reaction stops. So in this case, I started with only N2O4. Didn't lose very much N2O4, didn't make very much NO2 before the reaction stopped. All right, so with this system, I started with only products. So hey, this had to slide way back in order to get a whole bunch of reactants and lower the product significantly in order, again, to get to concentrations where they don't change anymore. So that's what equilibrium is. When the reaction stops, you have concentrations that are set. So it doesn't matter where we started, we end up with the same proportions of comparing the concentrations when I get to equilibrium. All right, the magnitude of the equilibrium constant, like I just said, it depends on temperature. If I change the temperature of a reaction, as we know, for example, the solubility of certain ionic compounds increases when you change the temperature. All right, so you're going to change the equilibrium constant if you change the temperature. The reaction will go further forward or less forward, depending on the temperature. And it also depends on the reaction. So some reactions you have a very big equilibrium constant, meaning that when the reaction stops, you made a lot of products, lost a lot of reactants. So this is true of ozone. Ozone turning into oxygen at that very high temperature has a monstrous K value, right? So 10 to the 12. So basically what this tells you is when this reaction stops, you don't have any more ozone. It's trace amounts, and you basically turned it all into oxygen. Or you can have very non-spontaneous reactions, meaning they don't go forward at all, barely. In terms of chlorine turning into chlorine radical, this is why we find, chlorine in nature is Cl2. It doesn't break apart to form Cl by itself very much. So the equilibrium constant is very small at 25 degrees Celsius. 10 to the minus 38. It's pathetically small. Basically, you just have, Cl2, very little chlorine radical. And some that are closer to what we'd call a K value of 1, where the concentration of the reactants is equal to the concentration of the products. And that's the thing a lot of people think. They think equilibrium somehow, when the reaction stops, we have the same concentration of the reactants as the products. No. That's a rare situation. I got to get the temperature just right in order to get a K value of 1. So most of the time you have a K value bigger than 1 or a K value less than 1. So this reaction is spontaneous, but not as much as compared to the disintegration of ozone. All right, so a K value of 5 means that, hey, I won't have very much reactants left, I'll have a lot of products.